It is my pleasure to introduce Luc Deike, who is an associate professor in the Department of Mechanical and Aerospace Engineering and in the High Meadows Environmental Institute. Luc, he arrived at Princeton in 2017, and prior to that was at Scripps, and received his PhD and bachelor's degree in physics in France. And so I think Luc, there's many things that you will see about him today. He is sort of a solid theoretician. His modeling is exciting, and he also manages to do really cool lab work. So sort of the trifecta there. And I think if you look at some of the awards that Luc has received, it sort of highlights the breadth or the way he does many things. He received a graduate mentorship award from Princeton University. So he takes our role as mentors and educators very seriously, and it shows. He received the Milton Van Dyke Award from the American Physical Society Division of Fluid Dynamics, and that award is an award that recognizes, yes, scientific content, and yes, originality, but also artistic value, right? And I think what really stands out with Luc is his creativity and really the beauty. You see the slides. If history is a sort of a way to predict, will be beautiful as well. And then he also received from the School of Engineering and Applied Sciences the Alfred Reinstein Award, Faculty Award for Young Scientists, and an NSF Career Award. So everything from the solid science award, mentoring, and incorporating beauty in what he does. And I think, one of the fundamental hallmarks of Luc to me is that he is serious, quiet, and generous, and really, really humble, right? If you spend months talking to him, unless you really listen to what he's saying, you wouldn't get a sense of how brilliant he is, to the point where he came... No, I mean, you have to listen to him, right? He's not, that you have some friends that they'll let you know that they're smart. So in fact, for weeks, I had this sitting on my desk, and I didn't take a time to open it, but I really wanted to open it. And Luc came in, and he didn't say anything. It turns out this beautiful cover article on Physics Today, how wind makes waves, a really fundamental question in oceanography and fluid dynamics. Luc was a co-author. Forgot to tell me, forgot to tell his department chair, because he didn't want to brag. It's fantastic. Anyway, Luc, go ahead.
Thanks a lot, Gabe. So now, now I have to live up to all these expectations. Thanks a lot, Gabe. Thanks for the introduction. Thanks for giving me the opportunity to talk today. So I'll be talking about work done in my group in the last few years on ocean spray aerosol emission and going from sea salt emissions to talking to microplastics towards the end of the talk. And sort of to introduce the topic, I tend to start with these pictures, which summarize what we've been going to be talking about for the next half an hour or so. So this was taken from a research vessel just after a fairly large wave has broken. And you see these white patches that corresponds to bubbles that have been entrained and that are going to contribute to exchange between the ocean and the atmosphere. And we can look at the same sorts of images taken during a winter storm in the North Atlantic with wind speed at 10 meter height, close to 25 meters per second. So that starts to be some serious winds. That's sort of the edge of what we would define in terms of tropical cyclone wind speed. And you see that the sea is completely broken up. You have like these very long streaks of bubbles, of white patches at the ocean surface. You see that you're going to have multiple scales of waves, some short ones, some large ones, and then drops and bubbles floating around. You see the spumes being transported on this movie. And it's these sorts of processes that we want to understand. We want to understand how they control the exchange between the ocean and the atmosphere. And that's really going to be what I'm going to be talking about today. So apart from the beauty of the problem, which might be a motivation in itself, there are some serious reasons to do it. So when you have these high winds, you're making these very turbulent flow that are going to very efficiently exchange momentum, heat, mass between the atmosphere and the ocean. And so you can think of a few precise examples of why it's going to be important. One of them, if you think about transfer going from the atmosphere to the ocean, is going to be gas exchange. So gas exchange is going to be enhanced by the presence of these bubbles that are being entrained. And so it's going to contribute to the carbon uptake budget, and it's going to dominate exchange of low solubility gases like oxygen. So I won't talk about this, but this is something we have been working on. What I'll talk about today is the other side of the exchange, so the emission of aerosols from the water to the air. They are going to contribute to momentum exchange, heat exchange, moisture exchange, and maybe more importantly for today's talk, production of ocean aerosols. So the droplets are going to be emitted either directly by the wind tearing or through these bubbles that come back at the surface and pop and emit small droplets. And when I say aerosols, I'm going to mean anything that's airborne and suspended in the air, in the turbulent air. And as these droplets then are transported in the air, they can evaporate and leave whatever material was inside. So it can be obviously sea salt, because the water has salt, dissolved salt in it, but it can also be biological particles, biological materials, and as we'll see towards the end of the talk, also microplastics. These aerosols are going to impact atmospheric processes. They are going to do so by affecting the radiative balance. That's a direct effect. And then they are also going to serve as cloud condensation nuclei. That's an indirect effect on the climate system. If you think about remote marine environment, like the Southern Ocean, then the sea spray aerosols are really important, because that's one of the main source of aerosols, right? If you are close to land, we are emitting, like close to land with cities and stuff, we are emitting tons of other things that might dominate. But if you are in pristine environment, then these sea salt aerosols are going to be particularly important. So that you can start picturing the range of sizes we're going to be talking about. This is a microscopic image. The little green curve bar is about 10 microns. So you see these salt crystals of sizes that are going to span a few hundred nanometers to tens of microns. So that's a problem statement that's been around for a while, but we still need to quantify these mechanisms emitting ocean spray aerosols, because you have tons of uncertainties and lack of fundamental understanding of some of the processes. So you have a large uncertainty on the absolute production flux. So this plot tells you the number of aerosols or droplets produced per unit ocean area per unit time for a certain wind speed. And so that's this number. You see a huge vertical scales in log with many, many orders of magnitude. And here the size with the peak of productions of sea salt around 100 nanometer or so. And then production sorts of like all the way through tens of microns. All the different lines are different studies from the field, from the lab, with various upscaling strategies, and they don't really agree one with the other, and they sort of make this very large scatter plot. And so constraining this uncertainty is really still something we're working on, or the community's been trying to tackle. The overall uncertainty, if you do the global budget of sea salt emission, is estimated to be around a factor 50, so that's quite a large number. So that's the first reason, trying to better constrain these number of emissions. Another one, which is sort of one of my favorite one in terms of uncertainty, is the role of sea surface temperature. So if you look at this plot, which shows the normalized concentration or flux of emissions as a function of temperature, you see that some data are showing that you have a production of aerosols that goes down by an order of magnitude when you increase temperature. And then some others sort of show the opposite trend with an increase in production when temperature increases. And so if you pick one curve or the other and you plug this into a climate model and you run it forward for a very long time with the temperature that increases, you're sort of obviously going to get very different results. So, and that's really related to the lack of fundamental understanding. Like we don't, or until this, there was like no real knowledge of and there are some reasons why these studies sort of, it's not that the data don't make sense, it's more like that the way people are comparing these data doesn't make sense, but you can parse it out if you go back to the processes. A final reason to look at the mechanism for production is the composition. It's been shown by chemists, sort of pioneering by Kim Fraser at UCSD, that the composition of the sea spray depends on the way the droplets are being produced. So if the liquid originally comes from the very thin film between the bubble and the atmosphere, it's going to be very much enriched in biological material. And if it's coming more from the bulk, it's going to have less biological material. So again, if you want to like tell the chemical composition of the aerosols, then you might need to go back to the production processes. So, so with all of that, we have very good reasons to like spend time, energy, and people on this problem. And so it's a problem that goes through a very wide range of spatial scales. So like the aerosols at the end of the day are as small as about 100 nanometers. And the wave system is going to be spanning kilometers, and the wind forcing is going to be characterized by even larger scale. But and so the way we have been looking at this is by decomposing the problem into three pieces, three sub-problems. My large-scale problem is going to be understanding a wave field forced by a turbulent wind, and so it's going to be, say, from meter to kilometer. And I'm going to be counting breaking waves. So I want to know in a certain patch of ocean how many breaking waves there is. Once I know this, then I want to know how many bubbles are being entrained. So I'm going to turn to the physics of an individual breaking wave. So the first subproblem, I'll look at it mostly statistically. The second problem, you can start tackling it dynamically by doing simulation and lab work. And then once you have counted the bubbles, then you go to the individual bubble processes. And so this one is going to be around the meter, and then you turn to a micrometer or millimeter scale for the individual bubble bursting process. So we're going to do that in the next 20 minutes or so. And I'm going to start by talking how you go from the wind to the waves and to wave breaking. So a very short introduction on wind wave physics. You have wind blowing over the water surface. You have a turbulent airflow, so you have a certain wind profile, that's turbulent boundary layer. You have turbulence, you have a mean flow, and it's going to force the motion of the waves. And these waves are going to span a wide range of scales. So if you look at the Carnegie Lake, where the wind starts blowing, you're going to start seeing small-scale features, centimetric features that start appearing and growing. And so that's sort of this picture with centimetric waves. And if the wind is sustained and keeps blowing over an extended period of time and distance, then you grow a mature sea state with very large waves up to hundreds of meters. That's going to be called swell, and then a whole range of spatial scales and the associated temporal scales. So the waves take their energy from the wind. They grow, and then if they reach a certain amplitude, sort of a certain threshold, they are going to break and dissipate their energy. And so you have really two physical parameters that are going to be essential to describe the wave dynamics. One is the speed or the wavelengths, which are really going to be tied up, and the other one is going to be the amplitude or the slope, which is going to tell you whether or not they are going to break. This can be summarized in a wave energy spectrum that gives you this range of scales. And so if you're familiar with turbulence, it might look a bit like a turbulent spectrum. You have the peak of your spectrum where most of the energy is contained. That's going to be a few hundred meters in most cases. And then sort of like two sharp power laws that tells you how the energy is distributed through the scales as you go from hundreds of meters to centimetric scales. And this can be observed in the field using LiDAR technologies, airborne or on platforms, and it can also be modeled in an operational way. And then what really interests me is counting not just the waves, but the braking waves. And so this is, again, possible in the field by flying aircraft and using imagery. And so this is a movie of a large braking patch with the airplane moving in the opposite direction of the breaker. And if you have this, you can extract the overall length of the braking crest and track the speed of the braking wave. And what we went on is really trying to describe this link between the statistical description of the wave and the statistical description of the breakers. That was like one of the goals of Jarong's PhD, who just defended and is now postdoc in New York. And so what she developed is numerical methods where you can model a patch of the ocean and a broad-banded wave field. And what you see is this undulating surface with waves of various scales propagating, and the red dots that appear sometimes are when the wave is breaking. And associated with this, you have a spectra that sort of look the same as the one I showed before that characterized similar to what you have in the field. And from this, then you can quantify the number of braking events with this other metric, which is going to be the distribution of lengths of braking crest, with the most breakers happening at low speed. Low speed is a small scale, and then a few breakers at a fraction of the peak. And so with this, you can start, because you have a numerical framework and a modeling framework, you can start spanning different strengths of wave field. And so that's what this plot is. It's like simulation looking at wave field of different intensity. This intensity is characterized by the mean square slope, which is a slope integrating the full spectrum. And what you find is that you always have the same shape with just more and more breakers as this parameter is increased. And then once you have these sorts of plots, you can play games in terms of rescaling the data to put all the data onto a single curve that you can describe mathematically. And this gives you an empirical way of describing all your braking waves as a function of basically a single parameter. It might seem simple, but if you had tried to do that with actually field data, it might have been initially difficult, but you can sort of close the loop in taking the scaling developed through this modeling work from Jarong, and then you take an ensemble of field data collected by various groups. And so this is like this rescaled plot. Again, like this is, in a sense, the number of braking waves traveling at a certain speed as a function of the speed rescaled by this mean square slope. And you see that all my reddish points are right on top of each other. The other data sorts of span a certain scatter, but the point is that the scatter is reduced by quite a lot. And then the simple message that this tells you is that the wind really sets the waves, and then the waves sets the braking dissipation. And so you can, if you're giving me a certain wind field, then I'm going to be able to model the sea state and then the associated amount of braking wave. So that was the first part. That was my large scale. And now I'm going to turn to the physics of an individual braking wave, and I'm going to basically assume that I can describe all the braking wave in a self-similar way. So we can build on the last 40 years of work on braking wave, especially in the lab. That set of picture was taken at Scripps in a wave channel. It was sort of the typical experiment. You have a 30-meter long wave channel. You have a wave maker at one end. You send high-frequency wave first. They travel slow. You send low-frequency wave after. They travel faster. You tune their phase so that they meet in the center of the tank, and you get these repeatable braking events. Your braking event is going to be characterized by a certain speed and a certain slope. And so again, you get these two parameters that come back. And you see that you're entraining a nice cloud of bubbles. And so you can measure them and count them with high-speed cameras. So that sort of was the state of the field with some data on this. And what we did, which was led by Wouter Mustard, who has a postdoc in the group, now faculty in Oxford, is developing or pushing the state of the art in terms of the simulation that you can do. So these simulations, we solve the full native equations for an air-water system with the ability for the interface to break. I want the movie to play again. All right. What you saw, I'll try one more time. Okay. So you saw the interface getting to a breaking point and overturning, hitting back the surface. You see some drops being ejected. The color here is the vorticity field. And then when the underwater movie is going to start, you will see a tube of air being entrained in the water and then collapsing into a distribution of bubbles with small features and large features. Okay, so we have this, right? You're doing simulation, so you have all the data you want, so you can analyze these data. So I'll get back to this. But in a sense, we wanted to make the problem simpler. So you have the wave makes the problem complicated. So the assumption we made was that what you need to describe the fragmentation of the bubbles is you don't care about the waves. You only care about the fact that you're entraining an initial blob of air and you're putting it in a turbulent flow. And that's what this experiment from Dan was about. He is like turning quickly sorts of a scoop that's full of air, full of gas, and as it gets released, it enters a turbulent flow, so you have underwater jet, and so then the bubble gets deformed and break, and you can count everything. It makes the setup smaller. You don't need a 30-meter wave tank to do this. You just need something that fits on the table. And so then you can measure the bubbles, and you can vary the size of the cavity and look at what bubble size you're getting. So here you have the bubble size, and here you have the number of bubbles that results from these breaking events. If you inject your bubble close to a critical size that I'm going to describe in a bit, you see that you're just forming a few more bubbles and you don't get anything in that small scale rate. Sure. If you go to the yellowish colors, then you start with a bubble that's very large, that's basically this movie, and then you're forming like a whole continuum of scales. So it's a bit counterintuitive. If you start with a small bubble, you're only forming children that are of similar sizes. If you start with a very large bubble, you're forming a whole continuum of scales. And the critical scale that described this problem is called the Hinze scale. It was defined by Hinze in the 50s, and it's a stability size. So you take surface tension that holds the surface together, the strength of the turbulent flow epsilon and density so that your dimensions match up, you get a length scale. And so if your bubble is larger than this length scale, then the flow around is going to break it. If your bubble is smaller than this length scale, it's going to stay stable. And so the beauty of this is that you are getting the sense that, so if you start with a bubble here, it's just going to sit forever in the turbulent flow. It's not going to break because it's stable. But if you start here, you're able to populate the whole landscape. You can sort of be more precise by going into numerical boxes, where again, you solve a single bubble in a turbulent flow. Here, it's a bubble close to this critical size, and indeed, it deforms and breaks into two more children. So you start from 1, you end up at 3. And here is a much larger bubble that then deforms very strongly and gets you tens of children. What you can see is that the deformation is quite different. This is sort of mild, and then it breaks. This gives you like these very elongated filaments that are the ones that actually produce the tiny bubbles. And so it gives this idea that you have two types of breakup processes to populate the bubble, this size distribution. A local process, which is sort of like the classic turbulent cascade picture, where you're filling the spaces close to your original point. And then a non-local process, which is non-trivial, where you start with very large objects and you're making very small ones. And so that we sort of then can analyze a bit in a theoretical way, and we can actually describe the scalings of these distributions. That was really done by Aliénor and Stéphane for the theory part in like finding an argument to explain this R minus 3/2, and it's related to the time scale of breakup of these filaments that are formed when you have very large deformation. For the other part of the distribution, it's a classic turbulent cascade scenario. It was described by Garrett in 2000. And what's really cool to me in this plot is that you superpose data that are from breaking waves, that are the black and the gray, so in the lab or in the simulation. And you also can put these sorts of more idealized case where it's just a cloud, or it's just like a big bubble and again, lab or simulation, you can put them all together. So you have sorts of a robust description of the problem. Okay, so I've done the waves, I've done the bubbles. Now I need to go to the droplet production because I promised aerosols. So we need to make the aerosols now. So we go to another lab experiment where we generate a population of bubble that we are going to be able to control. And then we're going to look at the surface, and then we're going to look at the drops that are being emitted. If you have good eyes, or if the projector is good enough, you should see droplet floating around. And this experiment might look quite similar to your glass of sparkling wine, right? You have a population of bubble going up, they sit at the surface for some time, and they pop, and you see tiny droplets. This is the top view when you have a broad distribution of bubbles. This is a movie done by Megan. If I manage to make it work again, and you can stare at it forever. It's very, very relaxing until you have to analyze the data. And so you can still, or Megan can analyze them, and you get the distribution. So you have your size distribution of bubbles at the surface as a function of size. And you recover or you engineer the same distribution than we describe for bubbles under breaking waves. And that's sort of on purpose, right? We understand the process, so we can just like reproduce it. So we have an analog for the breaking wave in the lab, again, in a reasonably sized experiment. And then we can measure the aerosols, so the drops. We're going to measure the aerosols. Yeah, these bubbles go from a few tens of microns to 10 millimeter. And then you can track down the whole population of droplets that's created by these bubbles. And the largest one are going to be a few hundreds of microns. You're going to be able to measure them with direct optical techniques. So holography or shadowgraphy. This is all like, if it's above 10 micron, you can get it directly optically. For smaller stuff, you're going to need to do something a bit more indirect. And so you have instruments that are used in the atmospheric science community where you suck the air and you recover the drops and you dry them out and you measure whatever solid particle is left once you have dried your droplet. And so if you have a solution of sea salt, what you're getting at the end is a measure of the size of the salt crystal. You don't have the composition, so you sort of have to trust that you really only put sea salt in your system. There are other ways to get the chemical composition, but we're not doing that yet. And so we have two instruments, one that covers a sub-micron and one that sort of does the 1 to 10 micron. Yeah. And you can link the droplet size and the salt size by mass conservation, assuming that as the droplet evaporates, it leaves a single salt crystal. So we want now to understand this blue curve with individual mechanism. So in the literature, you have sorts of two mechanisms described to produce droplet from bubble bursting. The first one is film drops. So when the bubble sits at the surface, it's separated from the atmosphere by a film. That film drains. At some point, it's going to open a hole. That hole is going to retract and form these droplets that are called film drops. And they are characterized, the way to characterize it is by thinking about the size of the bubble compared to the capillary length, which is about 2.7 millimeter for air and water. And there is a whole space of sizes around the capillary length where that process is supposed to work. The other process, which is really the one in sparkling wine, is going to be the jet drop. So once the film has broken up, you're left with a cavity. That cavity is going to collapse onto itself with capillary waves focusing in the center of the cavity and then emitting a jet that's going to form drops. And here, the proper fluid dynamics length scale to think about the problem is something called the viscocapillary length, which you get from combining the viscosity, the density, and surface tension. So you have posed the problem. You can go in the computer and solve it numerically. Again, you solve the water-air equations. With the free interface. You started with a cavity of about 1 millimeter. You get these capillary waves focusing towards the center of the jet. The jet is going to go up and destabilize into droplets. And you're going to get a few of those. And it's going to be about, so then you can measure the size of these droplets and compare different data sets. There are some of our data and some of other groups' data here. And you get this sort of master curve that if you plot the size of the drop divided by the viscocapillary length as a function of the size of the bubble divided by the viscocapillary length, you can describe the size in a very good way. And it's about a factor 10 between the bubble size and the droplet size. It's been looked at theoretically. That's a theorist in Spain that came up with a scaling theory. That's the black line, and it works quite well. OK, so with this, if you trust me, if you know the bubble, I can tell you the drop size, and I can also tell you how many there are, and we can also get the shape of the distribution, so we can combine all of this to construct the size distribution of drop for a given size distribution of bubble. So I'm going to start combining my snippet here. I have the size distribution of bubbles. That's my red piece. That's this part of the integral. And then I have the production of the individual processes. I integrate. It's basically a linear superposition. And I can then predict. I can then look at what this prediction looks like compared to the data. So if you do the jet drops, then you're quite happy because it really describes well anything that's above 2 micron. It gets the shape right. It gets the number quite right. So that's quite nice. You don't explain the smallest things. So you can turn to scalings in the literature for film drops. There are 2 modes described. And you sort of get the peak at about 200 nanometer, and you sort of get this transition here. It's not quite there, but let's say it's the right elements. So you can at least think that you can model this total distribution of droplet through the individual mechanism without really fitting the data. It's really like a direct approach. OK. So we have looked at these 3 sub-processes. We're going to now bring them all together to go back to the large scale. So you, again, write down a nice integral. Again, it's really just linear superposition of the different processes. So you count all the breaking waves. For each breaking wave, you know how much air is being entrained. For each breaking wave, you know the size distribution. And for each bubble, you know how many drops it's producing. So you integrate over c, which is the speed of the wave. So you integrate through all the scales of the wave, and you integrate through all the bubble size. If you do that, you construct sorts of like this, these blue and red curves, and you can compare them back to the results in the field. And what you get is something that's coherent, right? I'm not trying to make a claim that it's a one-to-one match. But you get something that's coherent from as close as the first principle as I could get. And so that's sort of like really encouraging in trying to then use that to large-scale models. And the variability induced by the waves explains part of the variability observed in the different data sets. Now that you have this framework, you can go and implement it in the global model. So we worked with Brendan Reichel and Fabien Polo at NOAA, GFDL. So they run operational wave model. So with a wave field that you get from reanalysis, you can compute the C state. So this is a map of the significant wave height, which is sort of the total, like a mean wave height. And then with everything I've been telling you, you can now compute air entrainment. And so once you have air entrainment, again, with the framework I described, you can do sea salt emissions. And so this is an annual mean map of the sea salt emissions, like cutting at 10 micron, and it's in mass. So it's the mass per unit area per unit time. And so you have a lot of sea salt emissions in the Southern Ocean where you have strong winds, and same at the higher latitude in the Northern Hemisphere. You would get this right with the sorts of like the parameterization that are in any global model right now. You would get a similar pattern. But again, the point is that you get it from a mechanistic construction. You can then compare the meridional profiles with other existing empirical formulations, and we end up with something that's actually very close to a formulation from 2003, the black and the dashed red. And it's quite different from like more recent ones. And the reason is that temperature dependency that I talked about at the beginning. Like the Jäger paper introduced a strong temperature dependency. Our mechanistic approach doesn't see any, or it sees a very weak temperature dependency. And so that's sort of the explanation and the point of discussion between these different lines. And so we're going to keep working with Brandon and Fabien at GFDR, and the goal is to plug this into an atmospheric model and see what we get. Okay, so that's where we are with sea salt. I promised microplastics at the beginning of the talk. And so now I'll discuss briefly how we can use these ideas and this framework to apply it to the emissions of microplastics. So the starting point of this was a conversation with a colleague, an atmospheric physicist at Cornell, Chi Li, who was a graduate from Ellie's group here, that said that there are observations of microplastics. So these are microplastic pieces going from like a few millimeter to much smaller things, like measurements of microplastics in the air, in places where you would not expect them to be transported directly from land. So like in Antarctica, they take sample of air, they actually find microplastic pieces. And so it sort of led people in the community of the atmospheric microplastic burden to think about whether there could be emission of microplastic from the ocean. And so that's this like, these arrows going up and down from the arrow going from the water to the air here, and this question mark. And so that brought the question, like when these people are trying to close their global budgets of microplastic movement from land to ocean to rivers or whatever, whether or not there should be a significant flux from the water to the air due to these bubble bursting. And you have a PNAS paper from 2021 that came up with a certain number with these sorts of inverse modeling approach. And you have several papers coming out that propose different numbers with different methods. And it's a bit of a debate because some papers say this is basically zero. That process is just not efficient. There are no pieces getting out of the ocean. And so the Yang et al. Paper basically says zero. And then you have a wide range of numbers in other papers. And so it goes from, so you have an uncertainty from 0 to 22 metric megaton, which is sort of an infinite error bar. And so we wanted to see, using what I have described before, where we would land, right? So to do that, we needed some data in the lab to know what's the efficiency of a single bubble to eject microplastic in the air. That was the end of Dan Show's thesis. So we went back to the lab. We put some microplastic particles in the water. We let the bubble burst. You see that the microplastic gets entrained into the jet. When you look at the movie of the jet, you see stuff stuck in the drop, stuff in the jet. So in principle, that tells you that this process can work, right? Anything that's in the water can get in the air through this process. So then Dan bravely took the drop on a correction plate, let the drop dry, and brought it to the microscope to count them, and did that for a wide range of conditions. And so it ended up with these sorts of plots, where you're counting the number of pieces as a function of the size of the particle divided by the size of the drop. And you see that you can have as much as 100 microplastic pieces in a single drop. And that corresponds to pretty high loading of microplastic, pretty high concentration of plastic in the water. And if you have a microplastic and small particles, and if your microplastic piece gets close to drop size, then it's more difficult. And you can also see a very strong correlation with the color, which is the concentration of microplastic. And you can revert the axis and plot this same number as a function of the microplastic concentration times the drop volume, and you see a very nice linear correlation, which is really the naive scaling you would have come up, right? You have the same, you You have the proportion of pieces you put in the drop is proportional to how much you had in the liquid. If you have nothing in the liquid, you get nothing in the drop. And that works as long as the drop size is larger than the pieces. So with this, you get sorts of an efficiency factor. And so I can go back, I take my machinery, I have my emissions of sea spray, and then I combine with estimations of the concentration of microplastic at the ocean surface. That's work from Eric van Zebbel in the Netherlands. And then I plug all of this together and integrate, and I end up with emission maps. And I get a global number, and we can talk about it. It's in the range, right, from 0 to 22. It's not 22, and it's not 0, and that's as much as we can say, I think. And so that's where we are, right? We have this multi-scale framework to look at ARC mass exchange. We can look at detailed fluid mechanics processes. We can put them together, and we can go and bring that to global model frameworks, and we can think of other aerosol problems. Thanks a lot.
All right. So for those of you joining us online, I will be monitoring the Zoom for questions. So feel free to enter them. And in the meantime, we will start with questions from the audience. We have a question back there. There's Mike coming along.
Thank you, Luc, for a nice presentation. So I'm curious about like when we use microplastics, that's a very broad term. So were there like specific type of microplastic that you consider for this?
Yeah, it's like it's an infinite problem, right? So we try to keep them spherical. So we bought spheres and we kept them neutrally buoyant. And that was it. You can think of surface properties, you can think of shape, you can think of anything you want, and like it's probably, my guess is that it's gonna change the scatter, but the mean is probably gonna be given more or less by spherical particles, but it could be wrong, yeah. But yeah, we only considered spheres, and we only considered near neutrally buoyant particles.
And also about after these microplastics are like transported into atmosphere, so did you also consider exploring how they are like retained in the atmosphere, like whether like after a certain point of time it will just maybe segregate from water?
Yeah, so you can look at what they become. One thing that I should point out about this, about everything I said, is it doesn't tell you anything about transport, right? I'm just saying what comes out of the water. And so the next big question is like, out of all of these pieces that come out, how many are actually transported high enough to spend some time? What's their lifetime? Because many of them are just going to fall back, but it doesn't change the fact that you need to start by a number that tells you how much get out. And that's part of the uncertainty for the sea salt and probably for microplastic as well, is that like usually, if you measure a particle concentration at, say, 100 meter or 1,000 meter, because you're flying an airplane with instruments, you are then, if you want to use this information to estimate how much is getting emitted by the ocean, you need to make an estimation of the vertical transport. And that one is a challenge in itself.
Thank you.
We have Wenchang.
Very nice talk. In the global model map, you showed, my understanding that it's like annual mean, like climatology of sea salt aerosol generated by bubble. Is that right?
So the emission for sea salt, we can do it as high resolution as the wave model is going to run, right? Because all the processes involving bubbles and turbulence are happening at much smaller scale in terms of time. So it's really going to be the resolution of your wave model, which is like, for everything I showed, it's half a degree, and it's, I think, 30 minutes.
Yeah. Thank you.
So you have the time evolution, and then you average out. Yeah. So sorry, maybe I missed your question.
Yeah, my question is, I'm wondering if you have looked at the like a synoptic scale maps, like showing if there are some impacts from like hurricanes in the tropical regions.
Yeah. So no, we haven't done it. It's part of the things that we would like to do. The wind product we use here doesn't really have the resolution and the frequency to resolve these sorts of extreme events. But that's it's been on the we have talked a few times with Gabe about doing that. We have done similar work about gas exchange, and it's the same question. Like we could look at it for extreme events. We haven't done it, but again, you need the right wind product, and then you can plug in everything we described. And again, there is a big caveat in this, is you're assuming that all the physics I described, which has been sort of validated for moderate to high wind speed, applies to hurricane wind speed, which again is also up to debate. But you don't know, you don't really have other options, so you might as well try with this.
Thank you.
I'm going to ask a question because there's other two questions, but you hinted at the question that I had. For very strong winds, sort of the view of the ocean as having a surface breaks down, right? There's no real ocean surface. You have an emulsion there. How would you modify the way you're thinking about this in that state? Is that?
Yeah. So great question. So it's something we're trying to look at with direct simulation of that two-phase process at very high wind speed. It's been postulated that when you go to hurricane wind speed, you're completely tearing down the interface. Whether or not that's completely true and at which scales that's true is like not completely clear. If you look at like the movies from like the sail drone that get trapped in hurricanes, you still see sorts of like a large-scale wave field. But yeah, that's like how much you can take these results and apply them to high wind speed is not completely clear. And we have a HMEI postdoc fellow working on it.
Yes.
Hey, thanks for a great talk. So you have those kind of global maps of aerosol emission from the three scales. Where at this point do you think the most uncertainty remains? At which of the scales?
It's a great question. I think it depends what you're interested in. If what you care about is the global mean number, then you're probably fine, and so I think you're just like putting one more piece into having a reasonable estimate. If you care about some form of like small scale variability, there are many possible ideas, right? Some people talk a lot about wind gust, right? Everything I talk about is sort of equilibrium between the sea state and the wind. There is the possibility that you have quite a bit of physics that's hidden when you have actually transient events. So I think you could argue that like surfactants are going to be super important, and then it's the small scale, right? That like if you actually have biological activity, all the small scale processes are modified, and so you have to change everything. So you can pick. It's difficult to say. I think that before refining these pieces, I would look at other pieces of the puzzle. So the vertical transport is sort of a big one for me, because if you look at what is used and done, that sorts of there's probably room for improvement there. So I don't know. Before continuing to dig a hole on this, I would look at other pieces of the puzzle.
Thanks for the very overarching work on all those scales. Going to even smaller scales, have you thought about interfacing your work with that of the cloud experiment at CERN that studies the effect of aerosols on the radiative forcing and other climate components?
Yes, so we have an experiment being developed in trying to look at that. It's sort of a separate problem, right? Then you want to take different types of aerosols and see how they might nucleate cloud differently. So yes, it's the direction we're going in. And we have been developing or building. Martin, that's like 2 steps in front of you, has been building a cloud chamber, and so we have the first results, sorts of, well, not results yet, but it's working. So we're making drops out of aerosols when in the proper condition. So yeah, that's something to look at. It's something that a lot of people have thought about and looked at in different ways. And
very interesting talk. Actually, my question is associated with the similar, another aspect of this study. So do you suggest decreasing the temperature of the surface, like surface water, because there is huge generation of like spray. So increasing the surface area will definitely decrease the temperature of the surface, right? So
sorry, say it again. I didn't get what you were saying.
The generation of these small droplets will increase the surface area of those drops, right? So it should cause, immense drop in the temperature of the surface of the water. So do you see, do you consider that as well for modeling? Because it will change the density.
I don't. So you are asking if if it's affecting the heat exchange or the temperature of the water as the drop get out?
Yes.
I don't think so.
Because
it's like at least you would need to bring out a lot of water to start changing the bulk temperature. But we can talk about it offline. I'm not sure I'm getting all the pieces of your question.
Thanks.
I'm being hypnotized by the picture behind you. I'm being hypnotized by the picture behind you. I see what I think are bubbles, and they're falling down and bouncing back up.
So
Am I wrong?
There are drops that are,
You're going back up?
Yeah, so under the right, so okay, this is the same movie than the one where it was looking from top that had all the bubbles popping, rearranging and popping. But that's the same, but with the same conditions, but with a side view. So you, like these sorts of blobs here are the bubbles, and then everything that's jumping up are droplets. And yes, under the right conditions, when the drop fall back, it can bounce. We actually have an experiment from French scientists when if you vibrate the bass, you can make the drop walk on water forever. So yeah, under the right condition, you are preventing coalescence.
Okay. Do we have more questions?
So speaking of that video, when I looked at it, I thought it was raindrops at first, and it made me think how important is rain in this whole process, because it looks very similar to some of the things you have mentioned, and there's a lot of it around the planet.
Yes, yeah, it's really funny because the rain, as you say, like there is a lot of rain over the ocean, and rain is always a very poor child in terms of the studies of air-sea processes. Like it's very hard to get data in the field when it's raining, so it's true. Yeah, it's like nobody really looks at it, like how much the fact that you have rain might entrain air again. You have exchange that's mediated by rain. As a side point, I think when you do, again, a bit like back of the envelope estimation, it rains a lot in the places where you have not so much wind, so it's sort of almost like two different things. So basically, I don't consider rain at all. If it rains a lot, then the bubbles might not be able to come back and pop. So yeah, I don't think I answered your question, but basically, we haven't looked at it.
So I'm going to ask another question because I thought somebody would, but I guess everybody else gets it. How do I understand a temperature dependence to this? It's not obvious to me. Is it through the surface tension or what?
Yeah, so the easy one is through viscosity. So seawater has a mild dependence on temperature, but it has one. So the cold water is more viscous than warm water. So because all the formula have viscosity embedded in it, you have a weak temperature and viscosity. But it's a weak effect. Like, it's really not an order of magnitude when you go from a few degrees to 20 degrees. So it doesn't explain at all the other lab data. And for film drops, you have, again, like when you think about the formation of the film drops, you have a weak dependence on temperatures in terms of the way the film drains and ruptures. So everything we did, we never found strong dependence on temperature, which worried me a lot for some time because I was like, okay, it really doesn't explain these graphs. It really got Rio Donner excited because he has other theory on why these scaling with temperature are just wrong. It's like he has, I'm not going to try to explain it because I will get it wrong, but it has to do with gust and convective events. So that it's the way the data are collected and integrated that makes it like they attribute a temperature sensitivity while it's something else that's sort of hidden when you do the attribution between your measurement and the I was going to say something else, but yeah, anyway. So, yeah, and there are also, like, if you look at the lab data, if you do, the way you create the bubbles, you can change your number of bubbles in terms of temperature, but that would sort of become a spurious effect of temperature. So there is also, like, just if you go in the paper and you look at where the temperature dependence comes from, it has nothing to do with the drop production. It's like something in the setup. So that's why these plots are misleading, because like you're really comparing things that you shouldn't be comparing.
Okay, well, I was just given the wrap it up sign. So we will, but please join me in thanking Luc again. And while I have you here, let me remind you, on October 3rd, we are going to have Mark Zondlo from Civil and Environmental Engineering giving us our second faculty seminar on the mysteries and challenges of agricultural emissions to the atmosphere. So put that on your calendar. See you then.